Hey guys, sorry I'm out of town today, so you're stuck with a sub and this video for notes. But we're going to start off fluid dynamics. In our previous classes, we've been talking about fluids when they're just kind of sitting still. But today we're going to talk about them when they're moving. We're also going to do that next class, and then we're going to start moving on into some thermodynamics. But as a side note, before we do that, if you would like to check your work, for last class, I am going to post the key for that in Google Classroom. So there's a freebie for you, but you're welcome to go check your work on that one and make sure that you're on the right track there on our buoyancy stuff. But today's topic is moving into the fluid dynamics. Things are going to be moving pretty quick. So some objectives for today here on this slide, we're going to calculate the flow rate of fluids, define units of volume, as if you didn't already know what some of those were, and describe things for incompressible fluids only, so that's liquids, not gases, and then talk about the equation continuity and kind of what it means and what its consequences are, because we're going to be using that one a whole lot next class when we start talking about Bernoulli's principle. So first off, now that we've got fluid flowing, that's the whole concept of the next couple of days. There's two types of flow. One of them we're going to study, one of them we're not, but you need to know what both types are. The first one is laminar flow. Laminar flow is nice and calm. It's constant. It's predictable. It's really nice and it's really smooth. And then the opposite of that is turbulent flow, which is constantly changing. It's very chaotic. If you've ever ridden an airplane and gone through a little bit of turbulence, you know that it can be a little bit scary and unpredictable. But laminar flow is that nice, smooth stuff. Turbulent flow is that kind of bumpy stuff going on. So you can see that here in this particular image. We've got some incense burning is what that looks like. Why the textbook chose this image, I don't know. But you've got laminar flow right here, right off the top of those where it's got a nice, smooth shape. That's more chaotic up here. Now, in our class, we deal with laminar flow only because it is nice, it's calm. We can deal with it with our nice algebraic equations and our calm, simple models. The turbulent flow, with all of its chaos, has to be modeled a lot more statistically and with some crazy math, and we're not ready for that. So we are sticking with laminar flow only, but you do need to know the name of laminar flow and what turbulent flow is as well. Another vocabulary word that you'll need to know is viscosity. You may already know this one. It's kind of how thick a liquid is, but its definition is really that it's an internal form of friction in the fluid that resists flow. So something like honey that doesn't flow very easily is highly viscous, whereas something like water that flows very easily is not viscous, or has a low viscosity. So it's about how easily something flows. Now, in my actual slides, I have a GIF. However, due to the limitations of the recording program that I am using, that GIF is not playing right now. If you want to go see it, you can go look in the slides, or maybe I'll edit it in here in post-production. But probably you're just going to have an image on the screen. Now, the meat of the matter today is flow rate. It's about how fast something is flowing. And we're not going to do any math that relates it to viscosity, but you can keep viscosity in the back of your mind as a concept. And this right here, ladies and gentlemen, is the flow rate. Unfortunately, flow rate does not really have a variable, which is kind of odd, but it does have an equation. This equation is not listed on your equation sheet because I assume AP thinks that you can figure it out mentally. The flow rate, or how fast something flows, is the change in volume, or the volume of liquid that flows through, divided by a specific amount of time that it flows through in. So it's the amount of volume going through in the amount of time that it flows. So that's the flow rate, not on your AP sheet. AP figures that you can mentally think your way through an equation for flow rate, but we're going to use it here in a second for some derivations. The typical units for this, for volume, is going to be meters cubed, and for time, it's going to be seconds. So your flow rate is going to be meters cubed per second. Now, what we're talking about today is mostly continuity, okay? So when we're talking about fluids, they're like actual matter, physical things moving through these systems of pipes or something like that. And because of the conservation of matter and just general logic, the flow rate has to be constant through a system. So, for example, if you have a wide pipe that has 5 meters cubed running it through it per second, then in the small pipe that follows it, like you can see here, here's the large pipe and here's the small pipe. If this first part is pushing 5 meters cubed per second, then the small part must also be pushing through 5 meters cubed per second. Otherwise, there would be a huge accumulation of water right there. And since water is not compressible, or liquid's not compressible, there's nowhere for it to go, and it would just build up and it would cause the thing to explode. And that's not what we're dealing with. That's not what's happening. So the idea here is that all of the liquid moving from the first section has to also be moving through the second section, and the rate at which it moves must be equal. Now, note that what I'm talking about here is the volume rate, not the velocity. Okay, not the speed. I mean the volume rate. And we're going to relate that to speed here in a second. To relate that to speed, we're going to have to do a little bit of a derivation. And to do that little bit of a derivation, I'm going to have to move my stuff over so I've got plenty of room. We're going to put that slide over there on the side. Grab the pen tool and start deriving. So what has to be happening here is that the flow rate, oh, I didn't grab the pen. Here's the pen. The flow rate in section 1 has to be equal to the flow rate in section 2. Oh, I forgot that one here. Okay, flow rate number 1 has to equal flow rate number 2. Otherwise, things would be building up, or the second pipe would be having to draw more liquid than was there. So the flow rates have to be equal for continuity's sake, because things have to be continuous. Our real world likes continuity. So what that means is that we can substitute in that little baby equation that we kind of thought through a second ago, where the flow rate is equal to the change in volume over the change in time. Now, really, these should all get subscripts 1 and 2 be equal, because whenever you have fluid flowing into and out of these sections, that's happening at the same time. So what we need to do is expand this out a little bit and think about volume. Volume could be rewritten in something like a circular pipe here as the area of the cross section times the length of your tube or your pipe or whatever it is. And this will be cross-sectional area 1. And then this will be cross-sectional area 2 times length over here for these sides. Now, something that we could do here is examine this length over time. Length over time is really, really similar to distance over time, which you might remember from AP Physics 1 or Honors Physics or regular physics or any physics that you've ever taken, or maybe you just have a general idea. Length over time can be rewritten as velocity. And this equation right here is called the equation of continuity, and it relates the area, cross-sectional area of a pipe to the velocity going through that pipe in 2 separate sections. Though this could really be generalized to 3 or 4 or 5 or 6 sections. You would just have equals A3V3 equals A4V4. You could continue this equation out indefinitely. But really, this is all coming from the idea that the flow rate has to be constant. And then also this is technically equal to the flow rate as well, because we got it from way up here and that's constant. So the flow rate is equal to the area times the velocity of any section of pipe, and it is equal all throughout any kind of pipe system. And here on this slide, we just have confirmation of that equation. It says the volume entering one part of a tube must be matched by an equal volume leaving downstream. And that derivation leads us to A1 times V1 equals A2 times V2. Now, this equation is on your AP sheet. You do not have to derive it again, but you do have to know that it is equal to the flow rate, which is not on your AP sheet. Now, a mathematical consequence of this is something that you have probably experienced, and I think this is another one of those GIFs that I have here in the slides, but is not operating on my thing. But it shows a really common phenomenon that you have probably even done at home with a water hose. So if you are, I don't know, washing your car or something like that with a regular water hose, no nozzle, anything like that, though this is the technology that a nozzle uses, there's a really easy way to make the water from your hose go further than, the limp little stream that comes out normally. And that is to cover the end of your water hose with your thumb. What that does is it makes the water go out faster. And it's not because it changes the flow rate. The stuff coming out of your water hydrant is still coming at the same rate. But what happens is when you close off half or 2/3 or however much of that nozzle, you're creating a much smaller area. So for the volume of water to get out that needs to get out through that smaller area, it has to go much, much faster. So if you have a small cross-sectional area, you end up with a really, really fast fluid. And if you have a large cross-sectional area, you end up with a slower running fluid. And you see this in rivers and streams too. If you're kayaked or canoed or anything down a river, the really narrow parts are the really fast parts and the very broad, wide parts are the slow ones. And that's because of that conservation of the volume flow rate. Going through those narrower sections to get the same amount of volume through, it has to go a lot faster. So that's a common phenomenon that you have seen in your everyday life. So to see a mathematical example of this, we're going to look at the garden hose again. It says a garden hose has an inside diameter of 16 millimeters. The hose can fill a 10-liter bucket in 20 seconds. Question is, what is the speed of the water out of the end of the hose, and what diameter nozzle will cause the water to exit with a speed 4 times greater than the speed inside the hose? Okay, so I'm going to make this a little bit smaller really quick so I have some space to work. We're going to work this out together. So first off, the information we have is we have the inside diameter of the hose. We also have how much volume it can fill in a specified amount of time. So that sounds something like the flow rate. And I know normally this would be a lot more interactive and fun, or well, I at least think it's fun. But today you just got to listen to me go through it. So our flow rate is equal to our change in volume over change in time. And we have both of those things. Fortunately, our change in volume is that we filled a 10-liter bucket in 20 seconds. However, there is a slight issue with this, and that is SI units. SI units. Oof. So for anybody that didn't know, a liter is 1,000th. Where's my pen? 1 liter is 1,000th of a meter cubed. You can convince yourself of that if you need to, using like the milliliters, centimeters conversion or something or another. But 10 liters is therefore going to be 1/100th of a meter cubed. So we're going to change this 10 liters to 0.01, which is 100th meters cubed. So you got to be really careful with those units because liters is not the SI unit. Now from there, we've got the question, what is the speed of the water out of the end of the hose? And we know from our previous deal that flow rate is equal to the area times the velocity, and this would go out for however many areas and velocities we have. We only really are looking for one here in one section, so we don't have to deal with any other portions of that equation. But we know our flow rate is 0.01 divided by 20, whatever that is, and it is equal to the cross-sectional area times the velocity coming out the end of the hose. So to find our area here, a garden hose is circular. We're going to do pi times r, which is the radius. We have a diameter of 16 millimeters, so our radius is 8 millimeters, which is times 10 to the -3 meters, and that is squared. And then we're looking for that velocity, so we'll have to divide by whatever pi times 8 times 10 to the -3 squared is on both sides. That'll cancel to give us velocity 1. And that's going to take me a minute to do because I actually have to calculate it this time. Y'all are there and I am here in my house. So I have to do my own calculating, and that kind of sucks. Really, I'm stalling while I pull up the calculator on my phone and type it in real quick. 0.01 divided by 20 divided by parentheses pi times parentheses 8 times 10 to the negative third end parentheses squared end parentheses. So I'm getting 2.487 meters per second. Now, y'all are welcome to fact check me on that and tell me if I am wrong when I get back to class, but that's the velocity that I'm getting there. Now, part B says what diameter nozzle would cause the water to exit with a speed 4 times greater than the speed inside the hose. Now, you can brute force this by multiplying this by 4. And then plugging it back in for a different velocity and finding a different area. You can brute force plug it in for that, or we can think about it a little bit on this equation. So our equation was area 1, velocity 1 equals area 2, velocity 2. But what we really want is for velocity 2 to be 4 times velocity 1. So we could sub that right in. That would make our velocities cancel. And I would say area 1 has to be 4 times area 2. So our new area has to be 1/4 area 1. To get an area that is 1/4 of the original, we would have to have the diameter. So that would be an 8 millimeter diameter hose. All right, and you can convince yourself of that one with a little bit more effort if you would like, but I'm not going to keep doing it on this video because it's 10 p.m. and I'm a little bit over it. Now that is it on fluid flow rate. Typically, I would teach Bernoulli's principle on this day as well, but I have decided not to because I'm not there, and Bernoulli's principle is a lot. If you have any questions on the content, Dane should be able to help you with those. And if he's not, let me know so that I can tell him he needs to work on his AP Physics 2 knowledge in order to be a successful peer tutor. But there is a practice that goes along with this. We'll check over it next class, and y'all be welcome to ask me all the questions you want to on that particular date. But you will be using our little continuity equation here all the time next class. Anytime you use Bernoulli's that we're going to learn, you'll have to use this little equation. So better to get on it today. Hope you guys are staying safe and warm. See you next week.